All right, thanks for the introduction, Jose. I know I'm the last speaker before lunch, so hopefully you can bear with me for just a little bit longer here. Like you mentioned, I'll be giving a presentation on some ongoing work that I have in collaboration with Bruno Torres and Eduardo Martin Martinez on dynamically obtaining localized quantum fields from a free field theory. So the quick outline for this talk, I'll give a little bit of an introduction. I'll talk a little bit about the formalism for classical and quantum scalar fields, or localized classical and quantum scalar fields. I'll do a little discussion on most people's nightmare on numerical methods. I'll show some preliminary results that we've obtained so far, and then talk a little bit about where we want to go with this project, and then some conclusions. So as we all know, QFT has been a remarkably successful theory up to date. But one of the main questions that we ask when studying QFT is how can one probe these quantum fields? Now, we've had a number of talks so far that have shown that UDW detectors have been used as incredibly effective tools in studying a number of different quantum field theoretic phenomenon. Well, with UDW detectors, we all know that they're non-relativistic. And so a natural question arises in what if we want to generalize our detector to a field theoretic probe. And as we just saw from Bruno, one of the things we can do is we can utilize localized quantum fields as our probe. And so that's kind of what we want to do in this project in a little bit of a different light. And we want to connect this class of QFTs to things that can be constructed dynamically. And really, we aim to answer how can one dynamically create a localized QFT and some of the consequences that arise when we do this. So the model that we'll be using will be just a scalar field. And so we'll start by just analyzing the classical case. So we'll have a classical scalar field, which we know is described by the Klein-Gordon equation. We'll be working in 1 + 1 to simplify some of our calculations. And we'll assume that this field is massless. And we'll implement a time-dependent confining potential well given by this v of x and t term. And so the general solution will just be written as a sum over as a wave equation, essentially, where these phi k's represent mode solutions to the above equation. And we just leave it very general. And so what you might ask is, well, what's an example of such a confining potential? Well, the example we're currently working with is the sum of arctangent functions, which is a smooth mimic to the finite potential well with discontinuous walls. And we can kind of see that over time, this is what we're growing. This is kind of how our potential will be growing, where A kind of controls the height of this potential. The little l controls the width of the minima. So this kind of right here is the value of little l. And the script L is kind of the speed at which this will mimic the finite potential well. So it's kind of how fast we'll go from this minimum up to the maximum. And so what we kind of expect is that outside of the minima, we have a classically disallowed region. And so we would expect that over time, and as the potential is growing, that the initial profile, f of x, will become confined within that minima of the potential. And we'll also need some ways to visualize this. And so one of the ways we can do this, we'll be showing some of the energy density plots of the field. And then as some sanity checks, we'll also be looking at kind of how the energy changes over time with the addition of this dynamically growing potential. So having looked at the classical case, we'll move on to the quantum case, where we quantize the scalar field from the previous section just using a canonical quantization, where we'll promote the coefficients of the wave equation that we saw earlier to creation and annihilation operators. And these creation and annihilation operators will satisfy the canonical commutation relations. And our quantum field will then satisfy this equation of motion that you see here. Now, this is an operator-valued equation living in a Hilbert space, which can kind of become a bit cumbersome to solve for numerically. And so we can kind of work around this by instead evolving the two-point correlator or Whiteman function of the field. Now, in our case, this will contain all of the necessary information about the field because we're starting in the ground state for a free field theory. And we also get the added benefit when evolving the two-point correlator that it satisfies the same equation of motion in both of its arguments, And so if we've created a numerical method to solve for the wave equation, we expect that applying this method to both arguments of the Whiteman function will yield good results for the evolution. So we do make a few assumptions for the numerical purposes. The first is we assume that the field will start in a cavity whose width L is significantly larger than the width of the potential's minima, in which case we're still effectively modeling an initially free field theory. And the other thing that we do is we'll regularize the two-point correlator to remove vacuum divergences by just smearing each of the arguments by some Gaussian function whose width will be roughly on the scale of the discretization that we use to solve the PDE equation of motion. So with that in mind, how are we going to go about actually doing this? Well, first off, all of the simulations that you'll see have been done in Julia, and they do ask for the recognition. And we start doing this by discretizing the spatial and temporal domains. So if we have a cavity of width L, we'll denote the grid points for the width L by these xi, and we'll evolve it for some time t, and we'll discretize that by points denoted ti. And we'll define the grid spacings as the distance between any two adjacent grid points in both x and in t. And we adopt a notation where our approximate solution will be written by this phi super n lower I, and it's approximately equal to the exact solution of the field at the point xi and tn on our grid. And just to kind of keep some consistency between what we'll be writing down, we define v super n lower I to just be the value of the potential at the point xi and tn. So we'll also need a way to talk about derivatives on this grid. So how will we talk about the derivatives? We'll use second order finite differencing operators that most of us have probably seen somewhere in an undergrad course. And those expressions are given here, where we just do a second order finite differencing in time and in space. And we adopt this formalism to the PDE system written in full here. So in our case, we prescribe some initial field profile f of x. We assume that our field has an initial momentum of 0, and that we will use Dirichlet boundary conditions at the edges of the cavity that we've implemented. When we do adopt this formalism, we see a discretized version of this PDE, which contains all of the information we'll need to actually set up and evolve all of our simulations. What this equation allows you to do is you can solve for the phi n plus 1 time step, and all you need to do is save any information you have about the two previous time steps, which we can see we'll need some time step just before, and we'll need the one initially before that as well. Using this, we can then evolve the PDE starting at a time of 0 all the way up until we decide that we don't want to wait anymore. And it's easy to show that under some certain restrictions for the value of delta t squared, this numerical method is stable. It doesn't start to gain spurious oscillations anywhere. The solutions are nice and smooth, and they stay nice and smooth if that's how they start. And we also define the solution convergence order using this equation here. And this is a necessary check to ensure that no numerical error has been pushed through the simulation, and that if there is any numerical error, we can assume that higher and higher grid spacings will force this away, and we can feel confident in what we're looking at when we do get any results out of our simulations. Now, all this notation means is if we define a grid spacing delta xc, we'll solve the PDE, and then we'll half the grid spacing and call this delta xm. We'll solve the PDE again. We'll half delta xm. We get a delta xf. Solve it one more time. And then we plot the ratio of these differences, and we do expect to see that at some point we do get a stabilization, and we can say that any numerical error will converge away. And what we find is that the method that we're using is indeed convergent, even in the presence of this time-dependent potential. And so we do have a solid confidence that what we're working with is working and not giving any extra error in our solutions. So with that, we kind of extend this method to the two-point correlator, and we discretize now both of its arguments. So we discretize x and x prime, and we denote these points in a very, very similar fashion to what we did earlier. the grid spacings will be defined as they were in the previous section, and we'll just take delta x and delta x prime to be equal, delta t and delta t prime to be equal. And we again approximate the 2-point correlator using the same notation. The only difference here is that we now pick up this m and j term to account for the primed arguments of the 2-point correlator. And now you might ask, well, how, if you have two time components, how are you going to actually evolve this in a similar fashion to what you did earlier? And the idea goes as this. You can fix a point. Let's pick x prime and t prime. So we're fixing the points in this second argument here. And then we'll evolve just the first arguments of the function using the same kind of wave equation evolution that we saw from the previous section, where in this case, we keep m and j fixed, and we evolve just the n+1 time steps in terms of the n and n-1 time steps. And this is just kind of an example of what it would look like. You would, in principle, have to fix at some point the xi and tn values and evolve in the primed coordinates as well. But just to kind of give you an idea of how this would work. Now, using this, we do have some nice preliminary results. And so for the classical case, I could show an example here where we start with this initially delocalized field profile within the cavity. It's just the sum of the first 5 modes of the cavity. And what we see is that this initially delocalized field profile, over time, as the potential grows, becomes confined within the minima described by that little L, which in our case is, again, just about 1/2. It's the same potential I showed you in the earlier slides. And we see that it almost looks as though the boundary conditions are now set at the minus, in this case, 0.5 and 0.5 values. And so we can actually see that our field has been localized within the minima of this potential. Now, what we can also do is, if this isn't fun enough to watch, and you like something a little bit more solid, we can look at the energy density of this system. And what we see is that in this plot, it's very clear that you have an initial delocalization across the cavity. And over time, as this potential grows, you start to see that the energy density becomes centered kind of within the middle of the minima of the potential. And as one more sanity check, we can plot the energy as a function of time, where we've just integrated over the spatial domain at every time step. And we see that, as expected, the energy does grow as the potential grows, and actually stabilizes, and we get no additional energy and no loss of energy if we turn the potential off, which I've done here at a time step of about t equals 10 light crossing times for the cavity. And we do see that we don't gain or lose any energy in the system after that potential has stabilized. We also have an initial test for the 2-point correlator, in this case without the presence of a potential, just to ensure that we're kind of seeing expected results. And so on the left here is the initial condition where we've smeared the 2-point correlator for the large cavity. And we can see over time kind of how this system evolves. And we do see, in this case, to be very clear, the t prime variable is fixed at 0. And we simply evolve in the first coordinate of the unprimed variables. And what we do see is that the maxima of this function over time does stay along the lines of x equals x prime and x equals negative x prime, which is kind of to be expected. And so what do we want to do with this? Well, we aim to utilize these methods to check the validity of the adiabatic limit by looking at the ground state of this localized QFT and comparing it with the ground state of the vacuum for the delocalized theory. And we would expect that if this holds, if we start in the vacuum, as this localized QFT is created dynamically, then we don't expect to see any particle creation happening because, again, we've started in a vacuum, and if the adiabatic theorem holds, we shouldn't see anything over time. We also want to measure the mixedness between any two localized canonically conjugate variables, which we define here, and they are also written exactly in terms of the 2-point correlator and the time derivatives of the field in that 2-point correlator. And we can measure the mixedness over time using this expression here. Now, what these two canonically conjugate variables can define is an effective harmonic oscillator particle detector. And we could, in essence, use these localized quantum fields as particle detector models in this case. And if we're able to decrease the mixedness, then these particle detectors become even better tools for protocols such as entanglement harvesting, where the lower the mixedness, the more effective as a detector model these localized QFTs will become. And that is what we would expect, is that as we localize these, the mixedness should decrease between any of these two modes. So what we've shown now is we've shown a toy model for how we can dynamically create a localized scalar field. We have numerical methods to study the effects of these localizations. We've obtained preliminary results on what the evolution looks like and how to obtain the evolution of the two-point correlator. And we're now in the process of adapting these methods to test the adiabatic limits and mixedness of any two field modes. Thank you.
Thank you so much for the talk. I just have a couple of questions, if you don't mind. First, if you could go back to the log convergence plot, right? So if you're, sorry.
There it is.
Yes. So if you're starting, or you're using a second order finite difference scheme, right? It seems that the order in the plot goes from first to second.
Yeah, so initially it does look as though it starts, first order, and we do eventually arrive at a second order convergence. The reason for this is when we discretize the temporal domain like we've done, the initial increase in the potential is much larger than starting with no potential, and so it does introduce a slight error in the way the solution evolves. However, what we can see though is that as that potential gets bigger, the changes become much smaller on the discretization. And so this does eventually converge to second order. And it still gives you the confidence that any of the numerical error that existed here over time will get pushed out and dampened out by the existence of the potential having grown to a large enough value.
All right, thanks. And just if you, because I've never thought about this before in terms of like trying to numerically run into any issues dealing with like coincidence limits or?
Yes, so initially that's kind of why we are, as first steps and first tests for this project, that's why we've kind of done this regularization. I believe I showed, yeah, it was just a little earlier. It's kind of why we do that regularization right here, is because this will, in this case, if you evaluate this integral, you can remove the divergences at the coincidence limit and get nice finite values everywhere, in which case you can now substitute this in as a well-defined initial condition for the PDE system, and you don't have to deal with the numerical problems of coincidence limit divergences.
Thank you so much.
Yeah, I think it's quite interesting. I'm just trying to understand a little bit more about what you're doing. So you've got this potential that's got a bowl and flat outside the bowl, and then it grows with time, correct?
Yes.
Now, does that stabilize eventually with time, or does it just indefinitely grow?
Yes. So what we in the I think I showed it a second later.
I saw it linear in T.
Yes. So the potential does grow linearly in T. We do stop growing the potential after a point. So in the cases of some of the simulations you saw earlier, the potential will grow up to a time of about 10 light crossing times, and then it stays at that value. Okay, so it grows for a bit, and then we... Yes, right? Yes.
Growing, I would think the energy would...
Yes, that's it. If we did keep growing it, you would expect to see the energy continue to get higher. We do stop it at some point, and that's kind of... We would stop it at that point and say, okay, this would be the localized field that you can now use as a particle detector.
So one other thing, if
We actually, Bruno and I actually just talked about this a couple days ago, that there could be some nice applications in cosmological settings. We haven't explored any of them yet, but I would be very willing to look into them in the future.
Yeah, yeah, I think that would be interesting to apply these things.
Quick comments about things that have been said. This regularization method has been used by Marcus House, Waterloo. People have developed methods like the blurring of the coincidence limited environment. It was studied. It was not that it works well and what the limits are. It's a very good method for this kind of thing. It actually has been used in cosmology. They have developed it to some scenarios. I haven't talked yet with Bruno and Boris about this, but they have been. I think that one thing that is that you said, but I want to emphasize to back here, what the intention of this particular, although this can be used for anything, but still the intention is, okay, what happens when you build a particle detector from a quantum theory? So you have a theory that is a field theory that is completely localized, and then I want to grow a potential so that I have a bound system, a system that is localized in space. So I want to build a particle detector. There was some work saying, well, the mixedness because of Rick's leaders here and mixedness is going to kill you if you do that. Here we can show that if you do it adiabatically and slow enough, you can actually build a particle detector out of a fully relativistic QFT dynamically. It's like, creating a potential, putting together your atom if you want. So that's what I'm doing. But indeed, these tools are, and Boris is becoming the expert of this, so these tools are expected to have many applications. And yeah, the regularization in particular of the Wyman is not new, it's not ours in a way. Even though it's been used in the past and it's been used in many scenarios, including dynamical spacetime.
So Siska's asking, could you please reiterate the relationship between the localization and mixedness? Does your characterization imply purity constraints or traveling wave speeds?
Sorry, can you repeat that? I think I missed some of what you said there.
Could you please reiterate the relationship between delocalization and mixedness? That's the first one. And then it also says, does your characterization imply purity constraints or traveling wave speeds?
To answer the first part of the question, as you localize this field, again, because you have that disallowed region outside of the minima of the potential, you would kind of expect that there becomes less and less correlation between the state of the field within that potential and with the state of the field outside of the potential. And so you would likely see a decrease in the mixedness between these different regions of the field. Can you repeat the second question again? Because I apparently seem to have a hard time remembering it.
Does your characterization imply purity constraints or traveling wave states?
Periodic constraints. Not that I can see now. I don't anticipate that this would imply any periodic constraints on the waves themselves. I would imagine that given the fact that we're using particular boundary conditions, that the same boundary conditions would be satisfied on the edges of the potential, or approximately the same boundary conditions satisfied on the edges of the potentials as well.
Let's